This is OwlUp, where learning happens in minutes, not hours. For a deeper journey, explore all our courses at owlup.co. Now, let's dive in. Welcome back to Chapter 3 of The Dance of Particles. In today's episode, titled The Strong and Weak Forces, Balancing Acts in Nature, we're going to explore the fascinating differences between these two fundamental forces that govern the very fabric of our universe. So, get ready to uncover how these forces keep particles in check and maintain the balance of nature. Let's dive in. Right now, inside your body, trillions of tiny nuclear events quietly decide whether the universe keeps making stars or runs out of fuel. In this episode, we'll step inside the atom's core and follow the invisible tug-of-war that lets matter exist at all. That quiet drama in your atoms doesn't stay locked inside you. Scaled up, the same rules decide which stars ignite, which ones die peacefully, and which explode so violently they forge gold and uranium. The strong and weak forces, acting on subatomic particles, end up writing the life stories of galaxies. Follow a chain. Tweak the strong force slightly, and the best-bound nucleus might shift away from iron 56, changing which elements are common. Nudge the weak force, and the sun's fusion rate and lifetime could radically change. Planets might never form stable crusts. Long-lived stars like ours might be rare or impossible. In this episode, we'll trace how these forces set cosmic budgets of stability and change, which nuclei can exist, how long they last, and how their slow transformations shape the chemistry that life depends on. Zoom out from single atoms, and a pattern appears. Nature runs on trade-offs. Where the strong interaction pulls hard, it stockpiles energy inside tightly packed nucleons. Where the weak interaction intervenes, it slowly edits those stockpiles, changing particle types and energy balances over time. That balance sets how violently stars burn, how supernovae seed space with heavy elements, and how long radioactive clocks keep ticking in rocks beneath our feet. It's less like a static blueprint and more like a live negotiation, constantly updating which forms of matter are allowed to persist. Stand at the line where forces almost fail, and the universe's strategy becomes clearest. Take iron 56, not because it's special by decree, but because a delicate bookkeeping of energy peaks there. Add nucleons to lighter nuclei, and the average binding per particle rises. Keep going past iron, and that average starts to fall. You can still assemble heavier elements, but you no longer earn as much binding energy back. That shift is why ordinary stars stop at iron in their cores. Past that point, fusion stops paying its own energy bills. To see how sensitive this balance is, push the system in thought experiments. Strengthen the strong interaction a little, and many light nuclei would bind more tightly, or in completely different combinations. Hydrogen might fuse too easily, shortening stellar lifetimes. Weaker strong interactions and crucial isotopes like deuterium could become unstable or rare, choking off the fusion chains that power stars like the Sun. Now push the other dial, the weak interaction. Its coupling, encoded in the Fermi constant, sets how often protons in stellar cores successfully convert into neutrons and release neutrinos. Turn that rate up, and stellar interiors would process fuel too quickly, flooding space with short-lived, high-luminosity stars. Turn it down, and protons could linger without fusing efficiently, leaving a cosmos full of dim, slowly smoldering objects and fewer heavy elements. These tweaks echo in quieter places too. The free neutron's 14-minute-plus half-life is long enough for primordial neutrons to be captured into helium after the Big Bang, but short enough that they don't dominate chemistry later. Change that half-life significantly, and you rewrite the initial ratio of hydrogen to helium, reshaping the cooling of gas clouds and the types of stars that can form. Even inside planets, the parameters matter. Beta decays in radioactive isotopes buried deep underground help keep planetary interiors molten for billions of years, driving plate tectonics and long-term climate cycles. Shift the weak scale, and some worlds would freeze geologically young, while others might never solidify stable crusts at all. One technology metaphor. Think of these force strengths like firmware settings in a vast, distributed network. You don't notice them in a single device, but alter them slightly and the performance profile of the entire system, stars, planets, chemistry, time itself, changes in ways you can't easily roll back. In particle accelerators, this balancing act becomes measurable engineering. At CERN's Large Hadron Collider, protons slam together at TeV energies, and detectors like ATLAS and CMS sift through the wreckage. When they count how often jets of quarks and gluons appear versus sprays of electrons, muons, and missing energy from neutrinos, they're effectively watching the budget decisions of the strong and weak sectors play out in real time. In nuclear reactors, fuel design must respect a similar ledger. Isotopes like U-235 are chosen because their neutron capture and beta decay pathways thread a narrow corridor between explosive runaway and a dead subcritical core. Medical PET scanners quietly rely on that same corridor. The isotopes they use must emit positrons on timescales tuned to hospital workflows and patient safety. Shift the underlying interaction strengths, and both collider signatures and practical technologies would need entirely different strategies to harness or survive the resulting physics. Tweak these forces, and entire technologies would need redesign. Waste-burning reactors, for instance, depend on very specific decay chains. Alter those constants, and today's spent fuel might look like a rich ore or a useless rock. Future neutrino maps of galaxies could act like weather reports for fundamental physics, revealing small regional gusts from new particles. Even encryption might one day lean on rare weak events as ultra-secure random keys if we learn to monitor them with enough precision. In the next decades, ultra-precise clocks, neutrino telescopes, and tabletop quantum experiments may start to hear tiny glitches in this balance, like static on a radio between stations. Your challenge this week? Whenever you see a periodic table, treat it as a frozen snapshot of an ongoing negotiation, and ask what would vanish first if the rules shifted. This was OwlUp, your daily step forward. To keep learning with structured courses and more insights, go to owlup.co. Until tomorrow!